So let me recap what we did in previous lecture. We essentially talked about doping in semiconductors. So if you take silicon, which is our model semiconductor, you have all those silicon atoms, and they are bonded covalently using those sp3 electrons. This is the diagram I am using extensively, but never confused. It is not a two-dimensional structure, it is a three-dimensional structure. And if one silicon is replaced by, let us say, arsenic or phosphorus, then we say that we have doped this arsenic here. So if you take a silicon material and then dope this arsenic through whatever processes, so 1 ppm or whatever amount, so your similar arsenic centers will be here and there in this silicon. This whole thing is neutral, but since arsenic is a pentavalent material, the outer electronic configuration for that phosphorus or arsenic, this will be S2P3. So there are 5 of them. So in this crystal structure, 4 will go into these kind of sp3 covalent bonding, but the 5th one will be there. Now also, since if you compare with all these silicons here and together with their electrons, the core electrons which are in the inner bands, then all these 4 bonding electrons and all those things. So this is a kind of charge neutral thing, and here you are bringing this arsenic. These 4 electrons have gone here and this electron is outside. So it's essentially, if you remove this electron from here, then you have a plus E charge here, an extra plus E charge here, because this was neutral, this arsenic atom was neutral, right? So everything was neutral here, so all those 4 electrons went here and then you have number of protons there, and together with this electron it was neutral, and if you remove this, which can go anywhere later, so you have a plus E charge here, an extra plus E here on top of whatever is the host electronic distribution, electron charge distribution or charge distribution. On top of that you have this plus E. So when this goes here, we say that it leaves a positive ion here. And this introduces new energy levels in that diagram, that valence band and conduction band diagram. We said that new energy levels are introduced here. Impurity levels. This impurity level is essentially the energy of this electron in the field of this plus E charge. So you can compare this situation with a hydrogen atom where you had a positive proton, a proton here. So hydrogen atom, you remember, and then electrons. So if this electron is in the field of this, you have energy given by minus me4 to 4 pi epsilon naught square h cross square n square. So this is bound by this energy, n can be 1, 2, 3, 4. In the ground state, n is equal to 1, and we say that it goes around, but now you know with all that quantum mechanical wave functions we have talked, it's not proper to say that it goes around and all that. You have a spherical cloud with certain charge density distribution as a function of r, but nevertheless this energy is minus 13.6 eV for n is equal to 1, ground state. And if you want to remove this, you have to supply that 13.6 eV to ionize this, right. So you can have this similar expression for energy levels of this electron also in the field of this. The same expression one can approximate by that with two modifications. One is that it is in a silicon crystal, and silicon has a dielectric constant of 12 approximately, 11.67 etc. So roughly 12. So it's here it is a free space, but here this whole space is this dielectric with a dielectric constant of 12, and so this epsilon naught here, should be replaced by that epsilon naught times the dielectric constant, that means 12 times epsilon naught. So that's one modification. It's not in free space, it's in silicon. And the second, which is somewhat more abstract, is that this mass of this electron here. So it turns out that if you have a periodic potential given by all this periodic structure of this silicon, if you have a periodic potential and then electron is in that periodic potential, then the movement of electron or the energy momentum relation of electron while it is moving in that is like a particle of somewhat different mass. Okay, so this crystal potential can help the particle to go, and the crystal potential can obstruct the particle to go, and that is approximated by taking some kind of an effective mass. The effect of that whole periodic potential is taken care of by putting an effective mass. If the crystal potential is helping the movement, then you will say that the effective mass is smaller than the real mass, or if it is putting obstruction, it could be more than the effective mass. And also for what purpose you are solving this, what problem you are solving, that will decide what kind of effective mass should be used for that particular purpose. So for our purpose, where we are talking of conductivity and these things, the effective mass of electron in this silicon structure turns out to be something like 0.26 times the mass of electron. Okay, so this mass of the electron which is here, this is for free space where the potential is only because of this, but then here the potential is because of the periodic structure also. You have all those silicons and this and that. So there this mass is to be replaced by this. So if you do the calculation, you can get what will be the energy of this particle, how much here it was minus 13.6 eV, and 13.6 eV was needed for removing this electron from the field of this. If I want to remove this electron from the field of this, how much energy will be needed? So that is that impurity level energy which is here, which turns out to be a few tens of milli-electron volts, and so these energy levels are created here. So that we discussed about the impurity levels. Nevertheless, this is close to this and of the order of k into T, and therefore these electrons which are there, they jump here and populate some of these quantum states in this conduction band. So, and similarly, if you put a trivalent impurity here like aluminium or boron, a trivalent impurity, then you will have a minus charge here. And you can also talk in terms of hole. You can do a similar analysis as if this minus charge is producing a potential, and that hole which is positive charge, that is in this field, and again that positive equivalent positive charge hole that is also in this periodic potential. So similar thing can be done here. Effective mass of the hole can be put, and that means the movement of electrons in the bonds. So that is the hole. So for that also you will have an effective mass, and you can do calculations from here. So this is the effective mass of electron. Effective mass of holes also one can write, which is somewhat different from this, but not very different, of that similar order, something like 0.36 or so mass of electron. So if you have a trivalent impurity here, you create energy levels close to the valence band, and holes are bound to that minus E charge through that energy. So those levels we talked about. Then if you have this pentavalent impurities, then this Ne becomes much larger than NH, which is your N-type semiconductors. And interestingly, Ne into NH does not change. So this is Ni square. And similarly for this P-type also, if you put this P-type impurity, let us say you put aluminium here, then you have a minus charge, minus E charge here, and you can say that a hole is bound to this, which is saying equivalently that one of these bonds is broken. Okay, since it is coming with one less electron, so there is a hole out here, and that hole is bound to this. And if you want to remove that hole, that means you want to put an electron and put there, then that much of energy will be needed. So that's the physical meaning of that. So if you do this, then the energies are created here, and these can jump here, creating the holes. And in this case you will have NH, which is much greater than Ne. This relation still holds, and this is your P-type semiconductor. Right? Now let me talk about conduction in this semiconductor. If I put a battery, if I join it to a cell and create an electric field in the material, how these electrons and holes are going to respond to that, and what kind of current will result. So let's first do it for a metallic wire. So recall how conduction takes place in a metallic wire. If you have a metal and then you create an electric field here by joining a cell to it or battery to it, then you have that drift velocity. We talk in terms of free electrons. This is an approximation when you don't consider all those band structure, etc. But in metals also, or good conductors also, you have that band structure, and that Fermi function is very much in action. So in the conduction band you have electrons, but then if they are being filled from below, especially at low temperatures, and then you apply an electric field, not many of these electrons are going to respond. Only which are close to that Fermi level, only they are going to respond. So those corrections must be there. That is why this band structure, band theory is needed for these conductors also. But essentially the idea is that you have electrons which can respond to these this electric field, and that creates some kind of a drift velocity. Okay, so you have a relaxation time or collision time, average relaxation time or average collision time, where the electron is moving, but after a certain time it gets scattered. So if it is a perfect periodic potential, no impurities, reputation is 100%, then it may go like a wave without any hindrance. But there are problems because of, first thing is temperature, all these ions are vibrating, so that kills that periodicity to little bit some extent. Then you can have impurities and varieties of centers from where it can scatter. So if the average collision time, or what is same as average relaxation time, after which it gets scattered losing its previous memory, if that is tau, then on the average for this time tau, this electron is responding to the electric field, and hence the acceleration, if I go for a very classical model, the acceleration is like E by m, and the velocity is E by m into tau. The velocity it gains before it gets scattered. Once it gets scattered through that interaction, then all this systematic velocity that it had achieved from electric field, that is lost. So again it starts from zero. That random motion is there, but on top of that this systematic motion because of this. So this is of that order. This is of that order. It's such a crude calculation that I cannot claim that it is E by m tau, or it is E by 2m tau, or it is E by 3m tau, but it is of that order, some constant times E tau by m. So that is the drift. It's called drift velocity. And if the electrons are drifting with on the average this kind of velocity, then you can work out, by the way, this is you also write it as E tau by m times capital E, and this quantity, so Vd is proportional to E. Okay, Vd is proportional to E. In this calculation, E tau by m, this is the proportionality constant. But even if all these approximations are not taken and better calculations are made, this Vd will be proportional to E. And that proportionality constant, whatever it is written as mu, and this mu is known as mobility. Okay, this is known as mobility. So this is this, and then you can work out that if you have you take some cross section here, and then you take another cross section here, take this length as Vd times delta t, then at t equal to 0, if there are n electrons which respond to E field, as I told, not all electrons are going to respond. You have all that Pauli exclusion principle and everything is there, but if these are the electrons which respond to electric field, these are the electrons which you should call free electrons. In that case, you can work out at t equal to 0 how many of them are here. So if this cross section is A, then A and then multiplied by this is the density. Okay, this is the number density per unit volume, number of these electrons per unit volume. So A times this Vd delta time T, this is the volume, and this multiplied by n. So these many free electrons are here. These many electrons are going to respond to this E. These many electrons have achieved this drift velocity, this. And all these are going to cross this cross section here in time delta t. So in time delta t, all these electrons, which electrons? the electrons which are here, in this volume, that means these electrons will cross this cross section. Okay, so you can work out what is the current. Right? Current is charge crossing per unit time. So the current will be N times A times Vd times delta T multiplied by E. So this is the current, this is the charge. This was the number of electrons. On each electron you have this much of charge. So this much of charge is crossing here in time delta T. Okay, so per unit time how much charge is crossing, that is the current, right? If you divide by area, it becomes current density. So the current will be this divided by delta T. This much charge is going in time delta T. So per unit time, how much charge is going through a cross section, that is the current. So this is the current. And if you divide by this A also, then this is I by A, which is known as current density J. So that is equal to N times E times Vd, and that is equal to N times E times, this Vd is mu times E, this is the mobility, Vd is drift velocity is mu times E, so you can put it here. So it is like this. So J is equal to N E mu E, and this is written as sigma times E, where sigma is N into E into mu, and this is called conductivity. And this is your Ohm's law. You must have studied Ohm's law as I equal to V by R. If you apply a potential difference V across some conductor whose resistance is R, I equal to V by R, this is how you must have studied Ohm's law. And you do this homework, you show that these are equivalent. From here you can get this, from here you can get this. So this is your Ohm's law. Now, in case of semiconductors, similar expression will be used. In semiconductors, you have conduction because of the electrons and because of the holes. So if you write J will be N times E times mu. So E and capital E can be taken out. Right, and then you have N and mu. So number of electrons and mobility of electrons plus number of holes and mobility of holes. So this will give you the current, and the conductivity will be Ne mu E plus Nh mu H. So although the current is because of electrons, those conduction electrons and the holes in the valence band, but in any doped semiconductor of practical importance, one of the two will be very large as compared to the other. We had done this numerical exercise in the previous lecture. If you have a P type, let's say N type, ppm doping, 1 ppm doping, this is what we did. 1 ppm doping of arsenic or phosphorus in silicon, and we saw that the number of conduction electrons is of the order of 10 to the power 16, whereas the number of holes was just 4,500. So number of holes is so small as compared to number of electrons that the contribution is coming only from this part. And similarly, if you are doping trivalent impurity, then the hole concentration will be so high as compared to the electron contribution, number of electrons, the density of electrons, that concentration of electrons, so that only this will be effective and this will be totally negligible. So we talk in terms of majority carriers and minority carriers. In N-type semiconductor, electrons are majority carriers. Okay, so N-type semiconductor, these electrons are majority carriers. And for P-type, these holes are majority carrier. And the other one is minority carrier. So whichever is important, one can take that. And the mobility is once again, mobility is for metal, we have seen that it is like E times tau time divided by m. So of that order you can take that for semiconductor also, but always remember that you will have to put effective mass in place of mass if you want to do some order of magnitude calculations of this conductivity. So that is how conduction takes place in doped semiconductors. Okay, so now we are prepared with all kinds of physical understanding of these semiconductors, doping and charge carriers and how they respond to electric field and so on. So from the next lecture I will be talking about applications, and the first and foremost device that will be used is called PN junction.